Hi, I'm Sarah Constant, and I'm working with Mark Reinhardt, and we're going to explain standing waves. Okay, so a standing wave is also called a stationary wave, and they happen in two situations. One with a medium moving in the opposite direction, and this one is if there's two waves with interference. A standing wave, if you have two waves with interference, so you have one wave, they look like a sine curve if you're taking calculus. And then another wave is reflected back at the same frequency, like that. This is why it looks stationary, like it will appear as if it's not moving. These points are where they don't move, and these are called nodes. And then these points where the wave is actually moving up and down, that has the amplitude, I'll call our antinodes. So these are both here and here, and that is where the amplitudes are. Now, these waves are created with interference or a medium moving in the opposite direction, and there are two types of interference. So the first one is called constructive interference, and that is when the waves have the same peaks and troughs. So for example, you have one wave that looks like this, and then a second wave that's moving the opposite way that looks like this also. So if this is like N, and this is also N, the new wave is going to look like this. They're just added on top of each other. And so this one would be 2N. And that's called constructive interference. Now the other type of interference is called destructive. And that's when the two waves have opposite peaks and troughs. So if that's one of them, the other one's like this. So they'll equal a flat line because they're going to cancel each other out by the positive amplitude and the negative amplitude. So that's the second type of interference.
Standing waves can only be created at a certain frequency. These frequencies are called harmonics. One can find the harmonic series, or in other words, any frequency at which a specific standing wave can be produced, by using a formula that we already know and this concept. Pretend that we have a standing wave here. That's the upside of the wave, and here would be when it's below the neutral zone. From this point to this point is called the length. It would be considered 1/2 of the wavelength. For example, if you had the other side of the wave here, this would be the wavelength, and the length is 1/2 of that. So L for length equals 1/2 times wavelength. Through this, we can find that wavelength equals 2L. Using a formula that we've already learned, velocity equals wavelength times frequency, we can adjust this so that frequency equals velocity times wavelength. Inputting this into here gives us that frequency equals velocity over 2L. Either one of these formulas is correct. This is called the fundamental frequency. The fundamental frequency is the lowest frequency at which a specific standing wave can be created. The harmonic series is the fundamental frequency multiplied by the number of waves created in a medium. So the frequency of n waves equals n, the integer, the number of waves in the medium, times the fundamental frequency, represented by f subset 1. This is true because f of n equals velocity over wavelength n. Once again, n being the integer representing the number of waves in the medium. This here is called the harmonic series. That determines the specific frequencies at which a standing wave can be created. If, let's say, we were to increase the length of our medium by pulling out one of our example slinky rings in class, that would cause the fundamental frequency, f1, to go down, therefore decreasing the frequency that needs to be obtained to create a standing wave for each integer. If we were to decrease the length of that medium, the fundamental frequency would rise, causing the opposite to happen. This harmonic series is one way to determine how a standing wave can
A real-life example of a standing wave is in music, especially in musical instruments with strings and hollow basses, such as guitars or violins. These instruments are especially good at demonstrating standing waves because they have two things that a standing wave particularly needs. The first thing is a taut string. This creates tension in the string and rigidity, which causes the string to vibrate up and down quickly. The second thing it has is a hollow interior. This creates a container for those standing waves to vibrate in and to be reflected back to create a standing wave that looks as if it is not moving. Again, like this shape. Now, another reason why these are good at expressing standing waves and good in music is because the pitch can be changed. One thing that can change pitch is if you change the material of the strings. For example, on a guitar, there are 6 strings, each with different heavinesses. Weights, not heaviness, weights. When you change the material, that changes the velocity, which from the formula we learned, that frequency equals velocity over 2 times the length of the wave, frequency will change with a different velocity. Frequency is what controls pitch, so a change in velocity will cause a change in pitch. A second way that pitch can change, the standing wave can change in a guitar, is if you change the rigidness of the string. This goes along with the same concept as the material. Rigidness affects velocity, so change in velocity equals a change in frequency, which equals a change in pitch. These are because a different standing wave will be created. So in theory, of the 6 strings of a guitar, if this one is the thickest and then they're different, you can change the frequencies are going to be different of these 6, but they'll also be different if you tune them here. So those are 2 ways that standing waves create different sounds.